other series?
Don't. Yeah. Don't worry about it.
That's good. Okay. All right. Hi. I guess we're ready for Anna's third talk. So here we go.
All right. Well, thank you. I guess last time I gave you the statement. So we want to understand why we have a tower of why the tower of modular curves with the level at P getting smaller and smaller gives rise to a perfectoid space, and why we have this Hodge-Tate period morphism. So just to remind you, the goal is, so we want to show that there exists a perfectoid space x star gamma p infinity, which fits in the following diagram. Well, for one thing, it's the inverse limit over m of x star gamma p to the m. It covers sort of the ground level modular curve, and it admits a map of adic spaces to projective space. This map is called the Hodge-Tate period morphism. Okay, so I want to tell you a bit about how to prove this theorem. So we discussed the statement and some features last time, but in order to see the proof, so I want to also recall the example. So if you have a tower xn to x1 to x0 of flat formal schemes with transition maps, essentially the relative Frobenius, so formal schemes over SPF ZP cyclotomic, such that the transition maps are relative Frobenius, then you can construct a perfectoid space by taking the inverse limit in the category of formal schemes and then taking the adic generic fiber. I guess the way that Jared described how you would do this if you start with a formal scheme. So xn, inverse limit over n, and then the perfectoid space x infinity is the adic generic fiber. So first you turn this formal scheme into an adic space, and then you look at the fiber over SPA QP cyclotomic, ZP cyclotomic. And so this is the perfectoid space that you can get from this tower. So so the claim is that you can see something like this on a tower of modular curves. So basically, there's a part of the tower x star gamma p to the m. First, I'll just take gamma naught p to the m. So part of this tower has this structure. So you can see these spaces as generic fibers of formal schemes such that the transition morphisms between these formal schemes reduce relative Frobenius mod p. So reduce mod p to the relative Frobenius. So part of this tower, where just to recall, gamma naught p to the m, so you're looking at those gammas in sort of the compact open subgroup that we have at ground level, but such that at P you have this congruence condition, require them to be upper triangular mod P to the M, and the determinant to be congruent to 1, also mod P to the M. Okay, and so part of the goal of the talk is to make precise what I mean by part of the tower. So somehow you're going to end up breaking up this tower into two parts, and one really has a perfectoid structure that exactly comes from this kind of example, and one part kind of behaves exactly in the opposite way. And in fact, so I'm not going to say so much about this sort of thing now, but you're going to see, I think, something about this when the students doing the project for this mini course are going to give their presentation. Okay, so in order to do this, we're going to start with sort of kind of classical things. So we're going to look at just integral models of modular curves and look at their special fibers. So we're going to just consider, and so I'm really going to want to stick to simple things. So I'm just going to look at the ground level, gamma, and I'm going to look at level gamma naught p. So x gamma star with a bar, I'm going to take this to be the special fiber of the modular curve of the integral model. So there is an integral model over spec zp of the modular curve x gamma star. Okay, and this is something that has good reduction. So, I don't know, over spec fp. And x star gamma naught p, the same thing, but for gamma naught. And this one doesn't have good reduction, but it has semi-stable reduction. Well, the integral model has semi-stable reduction. The special fiber locally looks like curves crossing transversely. Okay, so let me draw a familiar picture. This is the Deligne-Rappaport model. So first, okay, at ground level, you have good reduction. This is going to be x bar star gamma. And then at level gamma naught p, what you have is two irreducible components that are each isomorphic to what you see at ground level, but that cross at certain points. These points correspond to supersingular elliptic curves. You have these two irreducible components, and then these points, you can also see them at the ground level. These correspond to supersingular elliptic curves. So I'll remind you what supersingular elliptic curves are in a minute, but say over FP bar. So you're just going to have finitely many points where these cross. This has one cusp that's labeled infinity, and so I'm going to label this at level gamma naught p. You have two cusps, one for each irreducible component, and I'm going to label the irreducible components by the cusps. So let's say this one is infinity, and this one is 0. Okay, so there's one more thing that I need to add to this picture, which is sort of the transition map. So just the forgetful map that goes down from level gamma naught p to level gamma. And just to remind you, the moduli interpretation here, so you would have an elliptic curve with gamma level structure. And upstairs, you have an elliptic curve with gamma level structure, but also with a subgroup. Okay, since I'm working, so all of this is over FP or FP bar. So I'm going to label special fibers with a naught. So an elliptic curve with a gamma level structure, and then a subgroup D naught inside the P torsion, a subgroup scheme of order P. Naught. Okay, and the map is just forgets this extra piece of data, forgets about the D naught. Okay, so I guess there's a map, one irreducible component and the other. And so I want to just talk a little bit about what these two maps are, because this is where you're going to see the different behavior at level gamma naught p that's going to propagate to gamma naught p to the m, and one of these will give rise to the perfectoid space that we're looking for. So, right. So even at ground level gamma, we have ordinary elliptic curves and supersingular elliptic curves. And those you can characterize in terms of the size of the, like if you look at the p torsion on the elliptic curve and you look at geometric points. So just to recall, if E naught is an elliptic curve over Fp bar, then the dimension as an Fp bar vector space of the p torsion in the elliptic curve, if you look at the geometric points as an Fp, yes, thank you, is less than or equal to 1. So the reason, in characteristic 0, this dimension is 2. Here, it would be at most 2, but the reason that you can actually bound it by 1 is because you have the Frobenius isogeny. On your elliptic curve. And the kernel of this is contained in E naught P. This is a connected group scheme. So you already lose, right, and this is of order P. So you already lose 1, and that's why you get this bound. And now, if you have 0, then you have a supersingular elliptic curve. If the dimension is 1, then you have an ordinary elliptic curve. So if it's 1, E naught is ordinary. And if it's 0, then E naught is supersingular. All right. And one comment that I want to make, because this is going to be useful for what we do later on, is that you can detect, for instance, whether E naught is ordinary. So you can see, that E naught is ordinary by checking whether the Hasse invariant of E naught over Fp bar is invertible. And this is something that you can do when you work with a family of elliptic curves. So for instance, I could take the universal elliptic curve over the open modular curve. And you can look at the Verschiebung isogeny, which is dual to the Frobenius isogeny. If you look at the map induced by V on differentials, determines Hasse invariant of E naught over this open modular curve. This is going to be a section in the relative differentials. You take the p minus first tensor power of that. So this is a line bundle on x bar gamma. And so the ordinary locus on the modular curve at ground level is the locus where this section is invertible. And this section vanishes at supersingular points. Okay, so that's another description of this stratification that we have in this picture. I want to make one remark because this is going to come up in my last lecture. If you multiply by the Hasse invariant. And you can take a modular form, which is a section of some power of this line bundle, to another modular form. It's a section of p minus 1 plus the initial power of the same line bundle. And if you multiply by this Hasse invariant, turns out this is something that's equivariant for Hecke operators away from p. So I'm not going to say more today, but tomorrow this kind of thing is going to show up. So remember that we're interested ultimately in understanding systems of Hecke eigenvalues. And so one way, and we're interested in starting, say, with a system of Hecke eigenvalues that occurs mod p to the n and lifting it to characteristic 0. Right? We've sort of reduced constructing Galois representations to producing such a lift. And we said that we want to do this just by constructing congruences. Well, multiplication by something like the Hasse invariant, multiplication by something that's equivariant for the Hecke operators is a very good way to do this and to produce congruences to characteristic 0. And we're going to see something like this that somehow, at the same time it's completely different, doesn't have the same kind of interpretation in terms of elliptic curves and this stratification, but something that is Hecke equivariant that behaves like a Hasse invariant tomorrow. Okay, so I'm going to go back to studying this picture. And so maybe, so I said that every one of the two irreducible components is isomorphic to the modular curve at ground level. So what does this isomorphism look like? Maybe it's easier. Let me go back to this slide. What does this isomorphism look like in terms of what the subgroup scheme of order P that you're carrying around? So in terms of that, how do you describe these two maps? That's a question that we want to answer. So this D naught, well, it could be the kernel of the Frobenius isogeny, or it could be different from that. If D naught is the kernel of F, so here you just have E naught and the kernel of F. Here you have E naught. So, kind of the transition morphism down to ground level is just an isomorphism. So, on the other hand, if you look at, let me see. Right, so this is the cusp 0. So if you look at X star gamma with X star gamma naught P, I'm going to label this by the cusp. So I'm looking at level gamma naught P, and I'm taking the irreducible component corresponding to the cusp infinity. So it turns out that this parameterizes an elliptic curve together with a gamma level structure and together with a subgroup scheme in the P torsion, D naught, such that D naught intersect the kernel of the Frobenius isogeny is 0. The other irreducible component corresponding to the cusp 0 is the one where D naught is the kernel of the Frobenius isogeny. So if you have something like this, then how do you show that this irreducible component is actually isomorphic to what you see at level gamma? Well, you can write down an isomorphism. This isomorphism is going to take an elliptic curve E prime here to the elliptic curve E prime modulo the kernel of the Frobenius isogeny on E prime and an induced gamma level structure. And the subgroup scheme of order P is going to be E prime. Maybe I'll put knots everywhere. So you take the P torsion and you mod out, again, by the kernel of the Frobenius isogeny here. So this is how you see that the irreducible component corresponding to infinity is isomorphic to the modular curve at level gamma. So because of this, somehow the transition morphism is sort of more sophisticated. Right. So the transition morphism here, I mean, this is still the forgetful map, but now the forgetful map, so you just remember the elliptic curve and the gamma level structure. So from what you have here, you go to E naught prime modulo the kernel of f and whatever you had gamma level structure. So if you think about it in terms of the map on at level gamma, then you can see that the map at level gamma is given by quotienting out. So on the moduli problem, it's given by quotienting out by the kernel of the Frobenius isogeny. And if you think about what that means, you can see that this map is actually the relative Frobenius. Okay, so that's, I don't know, yeah, if you've seen this before, then, you know, this must not be surprising, but somehow, right, this is the kind of dichotomy that happens when you go to level gamma naught p. So on one side, you get an isomorphism, and, you know, if this kind of behavior persists, it's going to be very hard to get a perfectoid structure if you have isomorphisms on FP bar things. But on the other one, you get the relative Frobenius. Okay, so what we want to do is we want to consider the anti-canonical part of the modular curve at level gamma naught p. The anti-canonical part is exactly sort of the part where the subgroup scheme of order p that you're parametrizing doesn't intersect the kernel of Frobenius, or a lift of this. So we want to lift this to characteristic 0. So let's consider, let's see. Let's consider an elliptic curve over ZP cyclotomic with reduction E naught. Then, so if you look at the p torsion on E naught, this fits into a short exact sequence. Kernel of the Frobenius isogeny is a sub, and the quotient is some G naught. So this G naught is finite étale group scheme. So because of this, this lifts to characteristic 0. So G naught lifts to characteristic 0. So we have this kind of behavior on the special fiber, but now we want to describe something like this at the level of formal schemes, and then, you know, possibly at the level of adic generic fibers. And so the way that you want to do is you want to try and kind of lift things to characteristic 0. It turns out you can do this. And so what you get is a short exact sequence So you have the p torsion in E, and you take G to be the lift of G naught, and then the kernel is going to be C, or I can also call it C1. This is the canonical subgroup of E of level 1. So now you have a notion in characteristic 0. You can consider a formal scheme x star gamma 0, or if you want, maybe more familiar notation is x star gamma ord. So this is a formal scheme over ZP cyclotomic, which is essentially the ordinary locus. More precisely, it's the p-adic completion of the ordinary locus as a scheme over ZP cyclotomic, which you can define by just taking sort of the open subscheme in your integral model of the modular curve, where the dimension of the p torsion is greater than or equal to 1 along the special fiber. Okay, so maybe this is a slightly complicated thing to consider, but you want a formal scheme version of the ordinary locus that you see on the special fiber. And you can do this, and you can do this not just for modular curves, but for higher dimensional Siegel modular varieties. So for Shimura varieties for GSP2G. Okay, so if you consider this, and you also have a canonical subgroup, then the picture that we have here, where the map is relative Frobenius, and we're working over FP bar, so we're working over the special fiber, has a canonical lift to characteristic 0. So in our tower of formal schemes, xn will always be x star gamma 0, so it'll always be the ordinary locus, and the transition maps will be certain lifts, canonical lifts of the relative Frobenius. So it almost seems that we're not doing anything, but I'm going to draw a diagram that hopefully, yeah?
When you say relative Frobenius, relative to what base?
Relative to FP bar.
Okay.
So you can, I need to define one more thing. So we have x star gamma, just the adic modular curve at level gamma. And inside of it, we can define x star gamma naught. That's just the open subspace cut out by Hasse invariant equal to 1. So this is going to be the ordinary locus as an adic space, just at level gamma. You can also define the ordinary locus at level gamma naught p, and you can define an anti-canonical part. So this is going to be contained in x star gamma naught p. It's going to be the anti-canonical part of the ordinary locus at level gamma naught p, and it's going to parameterize elliptic curves together with some gamma level structure together with D subgroup of the p torsion in the elliptic curve such that D intersect C1, the canonical subgroup at level 1. This is this canonical lift of the kernel of the Frobenius isogeny such that this intersection is 0. Okay, so now we have, just to remind you, we had this diagram that came from considering the irreducible component where the transition map is the relative Frobenius. This diagram now has a canonical lift to characteristic 0. So we lift this one. Can I, oh, I see. Right. Okay, so we can lift our diagram over FP bar now to characteristic 0. So we have X star gamma 0. So this is the ordinary locus at level gamma, but as an adic space. We have it at the ground level, and we have X star at level gamma naught p. We're only looking at the ordinary locus, but we're taking this anti-canonical part. So we're looking at elliptic curves that are ordinary, and the subgroup that scheme that you carry around doesn't intersect the canonical subgroup in more than just 0. So there's an isomorphism here. Here you have the forgetful map from level gamma naught p down to level gamma. And the claim is that the transition morphism here is a canonical lift of the relative Frobenius. And it's exactly the same idea. You look at the moduli problem. So what you have here, in order to construct such an isomorphism, you consider an elliptic curve E prime, and you map this to E prime modulo its own canonical subgroup. So maybe I'll say the C1 prime, and then the gamma naught p level structure will be given by the p torsion in E prime, quotiented out by C1 prime. So you have something like this. Now the forgetful map just takes you down to E prime modulo C1 prime. And so here your map is quotienting out by this canonical lift of the kernel of Frobenius. So mod p, this is quotienting out the kernel of the Frobenius isogeny. And so as a result of this, you do have the same kind of structure on the level of the adic space. And so, somehow, if you take now the formal scheme, you have a canonical lift of the relative Frobenius on the level of formal schemes. This gives you a perfectoid tower. So let me write this down as the upshot. There exists a perfectoid space X gamma naught p infinity. So we're working, so I've told you how to do things for gamma naught p. And I claim that this exact same argument also works for gamma naught p to the m if instead of just considering the kernel of the Frobenius isogeny, you consider the kernel of f to the m. And you can take it as an exercise to go through this for general M. And if you do this, you get a perfectoid space. So this is going to be X star gamma naught p infinity. It's just going to be the ordinary part at level gamma naught p infinity. We're taking ordinary locus. But then on the ordinary locus, we're also taking an anti-canonical part. So the anti-canonical part corresponds to, so you would have a subgroup, say inside EP infinity, but you just want the p torsion in D intersect C1 to be equal to 0. This is what it means to be anti-canonical. So there exists such a perfectoid space such that this is the inverse limit with respect to M of things at finite level. Okay, so you can get a perfectoid structure by considering these canonical lifts of relative Frobenius. Maybe before I move on to saying something more, it'd be a good idea to draw a picture. So, yeah. So X star gamma. Let's say that X star gamma looks something like this. So the corresponding adic space that specializes to, I guess, this good reduction thing we had in the beginning. Maybe I'll put this for a second up top. So this one specializes to this. You have, say, 4 supersingular points. These correspond to 4 supersingular disks that under the specialization map from the adic space to the special fiber of the corresponding formal scheme, reduced to supersingular points. And everything else is the ordinary locus. So X star gamma, 0. All right. And this specializes to the open, the complement of the supersingular points. Now, at level gamma naught p, well, you have, again, 2 components of the ordinary locus. So things are going to look something like this. So you're going to want to have your 4 supersingular points. Turns out these supersingular disks at level gamma naught p are going to become supersingular annuli. And everything else will be the ordinary locus. So everything else would be X star gamma naught p with a 0. But now there's a part that's anti-canonical. That's going to be this one. And a canonical part. That's going to be this one. So, right. And everything else is X star gamma naught p 0. OK, so this is roughly how the picture looks like. Now, if you go to level gamma naught p squared, you're going to get even more components in the ordinary locus. So that's going to kind of, your geometry is going to be more complicated, but you can always define an anti-canonical part by this kind of condition. OK. All right. So this is the first, I guess, example of a perfectoid structure that you can get on modular curves. But now we want to extend it to get, the whole tower of modular curves. So I'm going to try to explain how to do this. And so the next steps. So the first thing is that for any epsilon in, say, 0, 1/2, you can work with a version. So you can define an epsilon neighborhood of the ordinary locus at level gamma. This epsilon neighborhood is going to be an open inside the full space that is cut out by Hasse invariant, so an inequality on the Hasse invariant. We're going to ask that the valuation of that is greater than or equal to p to the epsilon. And so concretely what this means is you want to look inside these supersingular disks and go sort of, start out from the ordinary locus and go a little bit into the supersingular disks, but not all the way. This is what this X star gamma epsilon is going to look like. And I claim that if epsilon is in this interval, then any elliptic curve that is parametrized by this open inside X star gamma is going to have a canonical subgroup. So any elliptic curve satisfying this condition on the Hasse invariant will have a canonical subgroup of level 1. I'm going to call this C1. And what you want to think of this is as a lift of the kernel of the Frobenius isogeny. Now the problem, so once you're inside a supersingular disk, a priori it's not so clear how to lift things to characteristic 0. We use the fact that the co-kernel, if you quotient out by the kernel of Frobenius, what you're left with is something at all that lifts to characteristic 0 uniquely. So this is going to be a lift of this mod p to the 1 minus epsilon. And I'm just going to say that the point is somehow you can still define G naught to be the quotient of the p torsion by the kernel of the Frobenius isogeny, and this is et al. Mod p to the 1 minus epsilon. So you can, read Peter's paper or read the notes for more details on how to do this, how to approximate things for some epsilon. But the upshot here is that you get a diagram x star gamma p to the minus m epsilon, x star gamma epsilon, and x star gamma naught p to the m epsilon and t, where you have an isomorphism. You have just the transition map, and now this is a canonical lift. Of the relative Frobenius, but only modulo p to the 1 minus epsilon. So another thing is that when I had this tower of formal schemes, I wanted the maps to reduce mod p to the relative Frobenius maps, but in fact, you can do this with p to the 1 minus epsilon for some epsilon in this interval, or even 0, 1. Okay, and the upshot here is that you can extend your perfectoid structure to x star gamma naught p infinity epsilon and t. So this is going to be a strict neighborhood of the anti-canonical locus. So x star gamma naught p infinity epsilon anti is a strict neighborhood of x star gamma naught p infinity 0 anti inside the ambient space. I guess, well, for now I can only talk about it on the level of topological spaces, but inside this ambient space. So somehow this ambient space has part of it, you can identify some open in here with the underlying topological space of a perfectoid space, and this perfectoid space is going to be a neighborhood of the ordinary locus. Okay, so this was step 1. Don't just have things on the ordinary locus, but you go a little bit into supersingular annuli. Step 2 is go from level gamma naught p infinity to full level gamma p infinity. So I'll just say that in this case, what you need to look at is, so at level gamma p to the m, if you look on a neighborhood of the anti-canonical locus, which you can define just by pulling back from level gamma naught, so here, the maps are actually finite et al. And so the almost purity theorem tells you that if you have a perfectoid algebra over QP cyclotomic and a finite étale algebra over that, then that finite étale algebra is also a perfectoid algebra over QP cyclotomic. And so at every finite level, you just have these finite étale maps. So you have a perfectoid space at level gamma naught p infinity, and you add level structure gamma p to the m for every m. And then you get a tower of perfectoid spaces. Turns out that in the limit still gives you a perfectoid space. So let me just write this down. Sorry? That's an excellent question. So let me just say you use almost purity to show that x star gamma p to the m epsilon anti is perfectoid. So the question was whether this map is still finite étale over the boundary. And so one important thing is that for modular curves, the maps are finite étale even at the boundary. And you can compute cusps and check this. There's an exercise in the notes that asks you to do this. However, for, say, Ziegel-modular varieties, so for GSP2G, G greater than 1, the transition maps from level gamma 1 p to the m to gamma p to the m. So on x star, the anticanonical locus, you see ramification at the boundary. And so this is a very tricky point in the construction of Galois representations, and it can be solved, and you still use almost purity on the open space, but I'm not going to say more about it other than there is something genuinely hard to do in the higher dimensional case. But you can compute cusps on this anti-canonical part and check that you do have finite étale maps for modular curves. Okay, so that was step 2. Now you really have something at infinite level, gamma p infinity. You have a perfectoid space, except that this perfectoid space, so step 3. We have x star gamma p infinity, some epsilon neighborhood of the anticanonical locus. This turns out to not just be perfectoid, but aphanoid perfectoid. This is because these spaces are defined by some condition on the Hasse invariant, and the Hasse invariant is a section of an ample line bundle. So you can show that the space is not just perfectoid, but aphanoid perfectoid. Okay, now this space is contained inside, maybe I'll say the underlying topological space is contained inside the underlying candidate topological space that we have for our perfectoid modular curve. So this, I told you what it means for a perfectoid space to be an inverse limit of spaces in a tower. On the level of topological spaces is just the inverse limit. So the candidate space already exists. You just take the inverse limit of the topological spaces at finite level. So you have a perfectoid structure on some open inside the space that you're interested in. And then the next thing to do is to use a group action, the group action of GL2QP, to translate this perfectoid structure to cover the entire space. And so finally, you also have an action of the group GL2QP on the topological space, x star gamma p infinity. So use this action to translate. So you want to construct a cover by aphanoid perfectoids. Like if you construct a cover of this space by aphanoid perfectoids, then you've shown that it's a perfectoid space, like a cover as a topological space. So to just translate the perfectoid structure from x star gamma p infinity epsilon anti to everything, to the whole space. And so I'll say more about this next time. This uses the Hodge-Tate period morphism. So this is something that you can define on points, and I've told you how to define it on points. And so you just have to do some topology to show that GL2QP really covers everything. Okay. So I'll say more about the Hodge-Tate period morphism next time. So I'll stop here.
So in the interest of time, we'll postpone questions to the evening session. You can ask Anna directly, but people who are going on the field trip will need to have a quick lunch and get on the bus by 1:30. It's picking up at the hotel, but yeah, good luck.